the recording. So Paul, you were talking about the final, right? So let me just write it here. Final, I will give you the problems. This problem would be the problem sets would be given to you on Wednesday, this Wednesday. So Wednesday, as I said, we would have an office hour during this lecture time. We would have office hour, so you can ask me question, which is from 2:05, say to 3:05. Just 1 hour office hour we will have on Wednesday, and then during that time I will just post. I will be post as an assignment. An assignment on Canvas, and so I would give you probably about, let me just say about 8 to 10 problems, and most likely we will ask you to solve about 7 problems. Let's say 7 to 8 problems. So that those problems will be, some of the problem will be from the material. I mean, throughout the semester, from the material that have been covered by test 1 and test 2, and the other. It also include the problems that are from the material have not covered by chapter by the previous 2 tests, and the final will be due. I think our regular schedule time of the final is the coming Monday, right? I think it's from 2:45 to 5:45. Am I right? So you it would due on due on Monday, 5:45. Okay, so you will have plenty of time to work on it. Is that clear, Paul and Ryan?
Yes, thank you.
Yep, thanks.
You guys would have enough time to work on it?
Oh yeah, that gives plenty of time.
Okay, all right. So again, you two have been doing, even Hanwen as well, or 3 of you have been doing an excellent job. So don't worry about your grades, but I do want you to take this as an opportunity to relearn the material, review the material as you work on the problems, okay? All right. I actually has posted I just posted the lecture notes on, I prepared the lecture notes for today's lecture already. I already posted them on the Canvas side. So, but I will go over these again. So again, these are the homework problems for chapter 11. Now, so last time we talked about the Lebesgue measure. We talked about how to construct a Lebesgue measure. Today, what I'm going to talk about is the definition of Lebesgue integral. So let's first review what we talked about last time. What is a measure space? So a measure space is there are three things. One is a space. This can be a metric space, or even more general, but usually it has a topological space also fine. But here, you don't need to worry. You just assume that X is the Euclidean space, say Rp or Rn, or n-dimensional Euclidean space. Euclidean space. Now, then it has a correction. This M, this is the squib M. A squib M. It is a collection of sets, of subsets of X, which we call as measurable sets. This could be open set, it could be closed set. Actually, it's more general than that. Then there is mu is a set function. So for each of these sets, we assign a value to it. This value is non-negative. And this is what we call as the measure. It is a set function. Now, so this M, this collection of measurable sets, and this mu, this measure must satisfy certain axioms. So this M is a sigma ring. What is a sigma ring? Sigma ring means that it's closed under countable union. Countable union means that if you have, let's say, closed under countable union means that if, say, you have E1, E K, these to infinity, all of these are in M, are measurable sets, then the union E K is also measurable set. So, and then it is closed under set minor means that if E1, E2 are measurable sets, then E2 set minus E1 it is also measurable. So that is, this is what we call a sigma ring. Sigma ring in this case, sigma here just means countable. It means it is closed under countable union. Now, this mu is the measure. The measure keep for any set here, for any set at measurable set, you keep them a measure. You keep them assign it a non-negative real number, or infinity. It could be like if you have whole space, the measure whole Euclidean space, the measure in this case is the volume should be infinity. So that is why we take the infinity here. Now, this must be countably additive. What does it mean by countably additive? So that means that if EK are countable set, and then you look at the union, and this EK are pairwise, disjoint, then the union, the measure of the union should be the sum of the measure of each individual sets. So that is what we call as a measure space. Paul and Ryan, does this make sense to you too? Now the concept of measurable space, a measure space?
Yes. Yes.
Yes.
Okay, so a measure space is you have a space and you have a collection of sets which we call as a measurable set. Not every set is measurable. There's some weird set, very complicated sets. We will not be able to define the measure. And that actually is the key, one of the key ingredients of the Vega measure. And then for each of those measurable sets, we assign a value to it. But for these to become a measure space, it must satisfy the fact that these measurable set must form a sigma, what we call sigma ring, and this mu, this measure must have the countable additive, countably additive property. So that is the now. What is the Lebesgue measure? Then they actually have for a given space, you can define measure in any sense, in any way you want. I mean, as long as it satisfies those axioms. But in Lebesgue measure is the thing that we that comes from Euclidean space. This is and then this is kind of like generalization of the concept of volume to arbitrary Euclidean space, and define it in a way that is applicable to larger collection of sets. So first of all, in order to define the Lebesgue measure, we need to first define the Lebesgue measure for an interval. Interval here actually is just a cube. So it is, in 2 dimensions, it's just a cube. And in 2 dimensions is a rectangle. In 3 dimensions is a cube. I mean, one of these sides could be degenerate. So it could be like this. And this could be open. This I write here is closed interval, but this could be half open, half closed, or both open. But all of those we would just call it as intervals. So it's just kind of like abuse of terminology. Usually interval is just it's like this, but here we would also call this as interval, and a cube is as interval. Now, for an interval, of course, we can define we define the Lebesgue measure as the volume. Okay, so that is you modify the length of each side. So that is how we define. Now, of course, these are not the only thing we can measure the volume, right? So we want to generalize this as general as possible. We first generalize these to just finite union of intervals. Also, if you have let's say you have two, it's a union of 2 cubes. Of course, if they are disjoint, union of intervals, disjoint union of two cubes. How would you define? What is the natural way to define the measure, the Lebesgue measure of A? Of course, you just, as long as these cubes are disjoint, pairwise disjoint, you just define it as the sum of the Lebesgue measure of each individual intervals. So that is quite natural. Now, the problem is that this is still not quite not general enough to be useful. Or you can say, oh, I can only measure finitely many finite union of intervals, because I mean, a lot of stuff, of course, is not finite like this. It's not finite union of squares or rectangles, and so then we don't have a measure. This would not we haven't defined it in a general form so that it would satisfy the sigma additive property yet. So we define a measure which the Lebesgue measure on the sets of finite union of intervals, but we want to enlarge this collection of subsets, and then so that this would be our measurable sets, and then it would be a sigma ring, because this finite union of intervals, of course, is not going to be a sigma ring, and when you have countable union, then it is no longer finite. Now, okay, so to do this, I slightly changed the presentation from the textbook. So we define an outer measure. Outer measure means that So it's defined for any set E, not necessarily open, not necessarily closed, not necessarily. So for any E, we can define an outer measure. So an outer measure of this set is that okay, you just partition this into cover this by finite union of cubes. In this case, is squares, and then these are disjoint, and then you sum them up. Of course, this measure here, when you sum it up, the measure of the sum of the sum of the measure of the cube is going to be larger than the measure of the set here. But it's fine. We take the im. We take the im of all these sums. We take the im of all these sums, and then we define it as the outer measure. So outer measure is defined on any set. It could be infinity. Now, but the outer measure is not a measure. The outer measure now is defined on any set. Oh, this any set is too general. We can so and then this m star outer measure is not a measure. Why is it not a measure? Paul, what is that?
Yeah, I'm not sure.
Because it does not. This would not have the additive property. It would not have the countable additive property. It only have the sub-additive property, because you can get some examples saying that if you have disjoint union, you can have a disjoint union of sets so that this is not equal. This is not equal, but actually is less than or equal to. So you only have sub-additive property. In general, not countably additive property. So the outer measure is not good enough now. So this is a little bit different from what is in the textbook. So we define, instead of having arbitrary set in Rn in the Euclidean space as a measurable set, we restrict ourselves to what we call as Lebesgue measurable set. So a set is Lebesgue measurable if and only if you give me. Hi, Hanwen, you are late.
I'm sorry, I'm late. Yeah.
Yeah. But tomorrow I already record from the beginning, so you can go back to review the part that you are late. Okay.
Yes, I will review it.
Yeah. The most important thing is that I tell Paul and Ryan already. I will give you the final problem sets on Wednesday, and then on Wednesday we are going to have office hour from 2:05 to 3:05. I will post the problem set as an assignment on Canvas on Wednesday, and this is going to be your final, and then it is going to give you 8 to 10 problem and ask you to solve 7 to 8 problem, and then that final will be due 1 week from today at 5:45. Is that clear, Hanwen?
It's clear.
Okay, so then it would that is what we are going to do. All right. I hope all of you can come back again on at 2:05 on Wednesday. All right. So these are the go to forward. I may not be able to finish this if I cannot, but then you can read the lecture notes by yourself and also study the textbook as well. So a set is Lebesgue. This is the notation for Lebesgue measurable sets. If for any set A, you decompose A into two parts. One part is A intersection of the complement of E. The other part is A intersection of E. So then the measure of A, the outer measure of A, should be the outer measure of these and of these two sets. So that means that we restrict we now restrict the sets the subsets of Rn to Lebesgue measurable set, and because of this property, then the outer measure become additive. So that is then in this case we just define it the Lebesgue measure as the outer measure, but we restrict it to the Lebesgue measurable sets. So here are the facts. So if you have the outer measure of a set is 0, then it must be always Lebesgue measurable, because I mean in this case both of these left-hand side and the right. Okay, so actually you require proof. And then you can prove that this correction of set, Lebesgue measurable sets, is a sigma ring, and this becomes sigma additive, but not on all sets, but only on Lebesgue measurable sets. Okay. Ryan, does this make some sense now?
Yes, yeah, it does.
Yeah. Okay. So, okay, we first. All right. Let's just recall. Coming back. So we define the Lebesgue measure on the intervals. That is the generalization of the volumes, and then we from there we generalize it to define it on the finite union of intervals, and then from there we define an outer measure. Then a set is Lebesgue measurable if and only if you have the outer measure has these additive properties for any set A, and then this would force that now the outer measure would become a sigma additive on the Lebesgue measurable sets, and that is how one define Lebesgue measure. The textbook slightly different. Last time I give another version that is that a set is Lebesgue measurable if you can approximate by this by the sets from En from E I mean from the union finite unions of intervals. Okay. So now if we look at the definition from this way, it doesn't quite tell us what are the Lebesgue measurable sets, but we actually the following theorem give us more. So B, squid B are the family of Borel sets. What is Borel set? Borel set is a set that you can obtain by countable number of operations from an open set. let's say you have a closed interval, like from 0 to 1. You can, this is a union of, say, -1, +1n, and 1 minus n, all of this. So this is union of an open, of countable union of open sets. So therefore, because all open sets are Borel sets, and all closed sets are also Borel sets. So Borel set is a family that includes open sets and closed sets, and it's a lot more general than open and closed sets. As long as any sets that you can obtain by a finite countable operation from open and closed sets, and that it is a Borel set. Now, the Lebesgue measurable sets from this setting is just a Borel set unions a zero measure set. This is in M, this is in B, this is a zero measure set. So zero measure means that the outer measure of this is 0. So Borel set is a lot more generalized, general than the concept of open set, closed sets. And in fact, the Lebesgue measurable set is just Borel set and union a zero measure set. So that is that now this property gives us a sense of what is Lebesgue measurable set. It's a very general concept. But here I would not get into the detail. But you can construct a set on the real lines. You can construct a set on R. There is this a set in R such that E is not Lebesgue measurable. So there are sets that are not Lebesgue measurable. That interestingly, to construct such a set, you have to use axiom of choice. So then that is something from logic. So in some books, also for some mathematician, they try to avoid the use of axiom of choice. So in that case, then you will not be able to construct a Lebesgue measurable set, a set that is not Lebesgue measurable. Okay. Now, what is a measurable function? So before we can define a Lebesgue integral, we need to define measurable function. A measurable function is a function that is that could actually, it could take negative infinity, positive infinity. It's a real value. These are real value, and then also include negative infinity and positive infinity. Okay. So suppose E is a measurable set, Lebesgue measurable set, then F is a function, real value, extended real value function on E, then F is Lebesgue measurable. Here, it actually doesn't have all the concept that I talk here doesn't have to be Lebesgue measure. It could be any measure space, but for this class, our focus is on Lebesgue measure. Now, then is Lebesgue measurable if each of these sets is Lebesgue measurable for any real number A. Now, So this is a first observation would be continuous function are Lebesgue measurable. Why is that? Does any of you have an answer? So remember, what is one of the equivalent formulation of continuous is that for any alpha, this set is continuous, is equivalent to this set being open, right? But we know that these Lebesgue, all open sets are Lebesgue measurable. So therefore, this is a measurable set if f is continuous. So therefore, we said that measurable set, measurable function are a lot more general concept than a lot more general than continuous. In fact, let me just expand on this a little bit. Okay, so I will expand on this a little bit. So suppose I have this function. 1, 0. Now this function, is this function continuous function? Han-Wen?
Yes, it's continuous.
It's not. This is not continuous at any point, right? Because when it's irrational, it is 1. When it's rational, it's 0. So it's not a continuous function at any point. But f is measurable. Why? Because if you look at f greater than a, you would have several situations. If a is less than 0, so then this set would be R, because any value here is greater than 0. If a is less or equal to 0, if f is greater than 0, less than 1, so then this is only irrationals. Q is the set of rationals. If A is greater than or equal to 1, then this is an empty set. Now, all of these are measurable set. This R is always a measurable, the whole space measurable set. And this empty set is always measurable, and because measurable set is a sigma algebra, so therefore 2 is closed under set minus. So therefore this is also measurable sets. So all of these are measurable sets. So f is measurable. So a continuous function, you could have a measurable function actually is continuous nowhere. That is an example like this. Now, okay, so a measurable set, a measurable function is a function so that all of these sets are measurable. And then you can prove that if you have two functions, these are measurable, and then their linear combination or their product is also measurable. If you have a sequence of measurable functions, the inf of this sequence or the soup of this sequence or finite soup or finite inf or infinite soup or infinite inf, they are all measurable, or the lim inf and the lim soup are all measurable. So that is
excuse me, Professor.
Yes.
Yeah, what if a equals to 0 in this function?
Here.
Yes, is it R or something?
Oh, when a greater than this is R. When a is less or equal to 0, this is R. It's a set of all real numbers, right?
Thank you.
Why is that? Because if let's say a is 0, a is a is 0. I cannot let a equals to 0. I have to when a is less than 0. When a is less than 0, okay. Yeah, when a is less than 0, when a is 0, what happened? So, yeah, when this can be when a is 0, okay?
Yes.
All right, very good now. So, but this still the same. Conclusion is remains the same. Okay, all right, very good. Now, so, and if f is measurable, this function, we have f plus is the positive part, and f minor is the negative part. It is also measurable. So when you have a function like this, the positive part are these functions, are these parts. It is 0 here, is 0 here. This is f positive. Now what is f negative? Let me use here. So the negative, so you have you first you reflect it here. So this would be here, it would be 0 here, and this negative, it would be reflect. These are the reflect, and then this would be 0 here. So these are the negative. F negative. And you can see easily that a function can be decomposed into, when it's positive, I use positive part. When it's negative, I use minus of the negative part. This part is so become here, and then this here, this here become here. So it's negative part. So that is now. So this is useful because then if we want to start, notice that all of these functions are non-negative. So when we later on, when we're trying to define the Lebesgue integral for an arbitrary function, we just decompose into the positive part minus the negative part, and then we define the integral for the positive part and negative part separately, and then we just one minus the other. Then get us the Lebesgue integral of f. So that is now the way we define the Lebesgue integral is we first define it for simple functions. What is simple function? Simple function is just kind of like what we have as a step function. It takes only finitely many value, let's say C1, C2, C3, C4. So it is a function that takes only finite values, C1 to CL, say. Now, a characteristic function of E is a function that is, let's say this is E. We will define it equals to 1 on E, but equals to 0 outside of E. So that is characteristic function. Usually these use chi, I think it's chi E to denote the characteristic function. The textbook, I guess, it use another notation, but not chi, but this is more typical. So in this case, if C this we will let this set here as E1, this set here E2, and this set here as E3, and this set here as E4. Then a step function or a simple function is just a sum, a linear sum of the when x of the characteristic function of these sets. On this means that on E1 its value is C1, on E2 its value is C2. So that is any simple function is a linear combination, a finite linear combination of characteristic functions. Now one can prove that for any function, you can be approximate as point-one limits of simple functions. And if these are measurable, this simple function can be chosen as measurable. So a simple function is measurable, meaning that this set, all of these are measurable. All of these EI are measurable. And then if F is also positive, then this actually Xn here, K here can be chosen to be increasing sequence. So the idea actually is quite simple. This is an analytic proof here, but I would just say that if we let's have it and two let me erase this and then draw another one. Okay. Let's say you have this function. So this is now as k equals 1, let's say 1. And then in this case, you just first step is you divide this into two parts. So then you have this value here. Then yeah, maybe I would draw another picture so that it's not strictly increasing. Okay, so I decompose this into two parts. So then this would be in this case we don't have this actually should be k. Then I would have this. This would be my E1 1. This part. So you project this down here. This would make E11, and this part is also E11, and this this here, and this part is my E12. Now, so this on E11, I just take the value 0 here. I take the value 0 here. E12, I take the value this. So, but the next step is that we partition this into a thinner set. So we introduce this partition here, and then this become we decompose into 4 equal parts. So each part we have. Now on this, I would on this set here. These are from here to here. This would be my E21. This would be my E21. On E21, I use 0. But E2, this from here to here, this value here, it would be my E21, E21, 22. This is 2122. And then this part here, the value here would be my E23, and then my E24. So then on here, then I use this value, and on this I use this value here. As you can imagine, as I keep partition this, become thinner and thinner. These step functions. These are the step functions from here to here only. Would become closer and closer to the original function, and that actually is the analytic proof, and it's kind of like a precise proof of this. But as you can see, as you keep partition, so that actually is the key point of the definition of that would motivate us, the definition of Lebesgue integral. So on Lebesgue integral, instead of partition the domain into smaller parts, we partition the range into smaller parts, and then we sum up the area. So the area of these parts, and that is how it works. So okay, so now get back to this Lebesgue integral. So the way we define Lebesgue integral, first we define it for simple function. A simple function has only finitely many values. So you the Lebesgue integral of this is just the CI here times the volume of, because this equals to 1 on this set, so it is a volume of, or the Lebesgue measure of EI intersect E. Okay, so that is so again that is so that for simple function, essentially if you have this, it's just the area of the volume of these rectangles. But the thing that is different with what we learned previously is that previously we assume that when we do the partition, these are subintervals. But here, these are not subintervals. It could be any measurable set. It could be any measurable set. So now, for a non-negative function, we said that that is measurable, then the Lebesgue integral is defined as you approximate this from under. So here, if you want to look at this, so this is AB. So you partition the range, and then each of these would have, let's say this here, we have this, and then you approximate the area from under of this. Now let me just stress this point. The difference between the Riemannian integral and this Lebesgue integral is that when we partition the range, these let me draw another picture so that it becomes clear. So let's say this function here, if I partition the range, so then the intervals corresponding to this subinterval here are these values here, 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 here. So this, when you project this down, this interval, this interval, this interval, this interval, this interval. So it is a union of a lot of countable. I mean, it is a union of sets, and because we assume that this function is measurable. The good thing is that these sets are all measurable. All these rule sets, the union of all those rule sets are all measurable. So then you can define the volume, and then you just modify the heights of these, then gives you the volume under the curve. So that is the concept of Riemann of the Lebesgue integral for non-negative function. For any measurable function, the definition is slightly different. You just decompose, as I said, any function can be decomposed as the positive part minus the negative part. Then the Lebesgue integral of this function is just the Lebesgue integral of the positive part minus the Lebesgue integral of the negative part. And now, then a function is Lebesgue integrable if and only if the positive part and the negative, the integral of the positive part and negative part, both of them are finite. Now, if both of them are infinite, then we actually do not define. Infinity minus infinity is undetermined, so we do not define the Lebesgue integral. We just say the Lebesgue integral is undefined because in order to define the Lebesgue integral, we have to assume that at least one of these must be finite. Now, so this Lebesgue integral would have the same kind of property as what we learned in Riemann integral. For example, it has linear property and it has monotone property. However, and it has this kind of like a triangle inequality. However, it also has some other property that does not share by the Riemann integral. For example, any measurable function, and if it's measurable and it's bounded, then it is Riemann. It's Lebesgue integrable. So, like for example, the function that we just talked about, this equals to 1, and x is irrational, and 0x is rational. Oh, actually, it's 0 here and 1 here. It doesn't matter actually. Let me see. Yeah. Okay. Let me be consistent. With 1 here and 0 here. No. Okay. One here. One here, 0 here. Okay, this will be consistent a bit later on. So this function is Lebesgue integrable. It is measurable and it's Lebesgue integrable. The integral of this would be 0 because we have this property here. If a set has 0 measure and f is measurable, then the integral f is integrable, and then the integral of f is 0. But and we also another property is that if a function is 0 except on a zero measure set, all the set of all rational numbers is a zero measure set. We talked about that, and then so therefore this integral here actually will be 0. Okay, so one of the most important application of Lebesgue integral is the convergence theorem. So remember, when we talk about Riemann integral, we have one of the things that we want to understand is whether we can interchange a limit sign and integral sign. And for this, we need to have some assumption on the convergence of Fn. What was the assumption, Han-Wen?
I'm sorry.
When we trying to prove interchange the limit sign and the integral sign, we need to make some assumption in order to do that. What was the assumption?
Uniformly convergent.
Yeah, we have uniform convergence. But here for Lebesgue integral, you don't have to assume that it's uniformly convergent. But if let's say if you have a monotone sequence of function, if it converges, then you can always interchange the limit. You can always interchange your limit and integral sign, and no uniform convergence is needed. And we also have a Fadou's lemma, and that says that if you talk about lim im, and then you can always interchange the lim in side and the integral side, but you don't have equality. You have a one-sided, you have an inequality, and in general you have inequality. You always have inequality, and that is Fadou's lemma. And another theorem that is useful in the theory is what people call as Lebesgue's dominated convergence theorem. So that means that if instead of requiring Fn to be uniform convergent, we just need to have point-wise convergence, but you need to have that the absolute value of this function Fn is dominated by some Lebesgue integrable function. Then you can interchange. So this kind of theorem would not be true for Riemann integral. Well, for Riemann integral, we have some examples. You can go back to check to show that you cannot interchange the limit sign and the integral sign unless you have uniform convergence. We run out of time. I will not keep you. I wrote down the proof here. The proof here is that we first prove theorem 2, and then we use the Lebesgue's monotone convergence theorem to prove Fadou's lemma, and then use Fadou's lemma to prove Lebesgue's dominated convergence theorem. And then that is the proof I wrote down in the lecture notes, and I already posted on the Canvas side. You can read it. Now, okay, so for the, let me use 5 or 10 minutes of your time to just compare the Lebesgue integral and Riemann integral. So first of all, a Lebesgue integral is a generalization of Riemann integral. If you have a function is Riemann integrable, then it would definitely be Lebesgue integrable. And the Lebesgue integral is the same as a Riemann integral. So that is, now remember in a function is Riemann integrable if and only a boundary function is Riemann integrable if and only if what? Do you remember the criteria, Ryan?
The lower limit of, no, I forget.
we have a more specific criteria. It is a little bit different from a continuous function, more generalized, more general than a continuous function. But it can. Paul, do you remember?
For a Riemann integral?
Yeah, Riemann function, a bounded function is Riemann integrable if and only if what?
Right. The supremum of the upper estimates is equal to the infimum of the lower estimates.
Yeah, but this is the definition. We also have a criteria. We said that a Riemann integrable function is just a continuous. The set of discontinuity.
Oh, a zero measure.
Yeah, continuity has zero measure, right? Now, so this, if it is a set had this continuity, we already said that the continuous function is Riemann integrable. So this is the continuous. So the set is this is set of continuous, and then a zero measure set. So that is a set of discontinuous. So therefore, it is this is a bounded. This is a bounded measurable function. So therefore, it's Lebesgue integrable. So that that is so that is why you can prove this. This is you can find a proof in the textbook. The Lebesgue integral is a generalization of Riemann integral. So as I said before, you can actually, but however, the other direction is not true. You can have some function like this function, this that we talked about before. We know that it is not Riemann integrable. If I ask you to prove that this function is not Riemann integrable, how would you tell me? How do you explain it to me, Han-Wen? Why is this function not Riemann integrable?
I'm sorry, I don't know.
Because if you look at the lower sum, the lower sum would always be 0. The upper sum would always be 1. They cannot match, right? The lower Riemann sum would always be 0. The upper Riemann sum would always be 1. We proved this before, so it's not Riemann integrable. But however, it's Lebesgue integrable. In fact, the Lebesgue integral is 0. You can prove this by the monotone convergence theorem, or you can just prove it directly from the definition. Now, however, you can regard Lebesgue integral as an analog of Riemann integral, but instead of we partition the domain, we partition the range. That is what I meant here. When we do this definition here, we partition the range. So therefore, analogously, you partition. You don't use interval to partition the domain. You use measurable set to partition the domain. That is what it meant. Now, and then the last part is that for Lebesgue integral, we have those 3 convergence theorems that are quite more applicable. So you have a lot of application, because in general mathematics, it's difficult or it's impossible that this convergent is a point-wise convergent is uniform convergent. But a lot of times we want to interchange the limit sign and the integral sign, and that these convergence theorem become useful. So I'm a little bit rushed here. However, if you have any, go back to review the textbook and trying to do those problems. And then if you have question, then we can meet again on Wednesday during the office hour from 2:05 to 3:05. Okay, any questions?
No.
Okay, it's a big rush, but I hope you understand the idea. Paul, do you understand some the idea behind the Lebesgue indigo?
I think so. I'm gonna have to go back and review the notes though.
Okay, Ryan, tell me tell me some of the difference between Riemann indigo and Lebesgue indigo.
The discontinuities in a Lebesgue integral don't need to have zero measure.
Exactly. The Lebesgue integrable function are more general than Riemann integrable function. You have a lot more functions, and that make it useful. And okay. Hanwen, you have any question?
Do you have some homework of Rebecca?
Oh yeah, the homeworks are at the beginning. So these are the homework for chapter 11. I do not ask you to hand in any homework.
Yes.
So, but you can try these problems by yourself, and then we can talk about them on Wednesday if you want. Okay.
That's all.
All right, very good. So I hope to see you again on Wednesday. So take care, okay?
Bye.
See you then.